Okay, we're live. And as usual, Tara and Rohit are here.
Hello.
Hello.
Let's see. Last week. Okay, I remember. We just this. So the goal was to try and get a in-memory file system that could be set up via the file system. I think we'd gotten to the point where I could show that we could make a file system, mount a file system. Dance, apparently in Plan 9, it was called the clone dance, because this would normally be called a clone. But then once this file system is set up, we wanted to be able to bind it to a particular path, and that's what required getting into building this namespace file system. Now, I don't remember if we had it on stream, but at some point I had to deal with a recursion issue with some of the code that I made to put together these file systems. Because, well, let me show you. And also, they're basically working for the use case I'm talking about. I'll see. So we have fsys and proc. I think I renamed dev back to fsys in case dev being short for device. But in case not to confuse, because there's already a common /dev, so if we ever need to bring that back, I didn't want them to conflict. But let's see. So in proc, there's actually a actual process here, and if we cat self, it tells us that that's one. Oh, that's what it was. I had to overhaul a lot of context stuff as well in order to get it so that. Oh, and this will kind of help too. This is all cleaned up. So now there is a kernel struct that we can kind of put our two sort of core devices on for file systems and processes. And it registers an empty namespace process type. It won't actually create anything that we would consider a process, but it can at least create a namespace that would normally be used for a process. And go back to serve. We also register that hello-fs. And there's this new root, which is at this point allocating a process, a namespace process, which will give us a namespace. Yeah, now we have process with ID and a context namespace. So a root gives us something that looks like a process that we mostly use for its namespace, but what's giving us this file system is actually setting up two binds, because similar to Plan 9, these kernel devices, these kernel file system devices are actually hidden. So they use a hash prefix, so it doesn't show up, but the way it's set up is that that's how the kernel can provide a bunch of file systems that you can then put into a namespace. And if you don't want them in the namespace, you just don't bind them. So they kind of exist as hidden directories, and then you use bind to bind them to a non-hidden directory. And then bind is functionality that was not here last time, and that's part of the whole point of this namespace file. I don't remember if we looked at these tests, but just to give you an example, we can create a new namespace and then call bind on it, and then we can point at another file system and even a particular file in that file system, and then give it a name in the namespace. And then this file system now has bound file, which comes from this file system, file 1. Bound file, and it's got contents 1. You can also do directories, so testfs. Root is basically this as a whole directory. So then that's bound into the namespace as bound directory. That means we can now read bound directory and then any of the files from this file system. And that's the basic idea. There were some interesting does file bind over bind. So here there was a bug where if I did a bind, like I took this file system sort of as a directory and then mount it at the root of the namespace, that now makes the namespace now have these files at its root. And then I bind from another file system another name here, C, as C in this namespace. And originally there was some bug where that didn't work. If I bound root, it would ignore other names. So there were just a bunch of bugs. Here's the recursive subpath example that I ran into. So let's say we create a namespace, and then we'll create a file system here. It's got, control file and an NS file, and the NS file points back to the namespace. Then we create another file system, and it basically mounts a loopfs. So there's, and then we bound rootfs to the root of the namespace. So basically now in the namespace, we would have inner, and inside inner, we have CTL and NS. But then inside NS, it will go back to the root. So there's recursion there. We could then go to inner again, and it just kind of keeps going if you keep going into NS. And that's the type of thing where you can go into a Stack Overflow, because it just keeps, calling. I think the bug was one of these maps would, if you just do a stat to find out, is this a directory, that it would call stat on all of the children. And if that's the case, then it sort of recursively calls stat on everything. the entire tree. And if it eventually gets to something that loops back, then it will just kind of continue calling stat forever. So I had to do something to break that loop. I don't want to get into that. There's a bunch of little things to get all of this working. Anyway, so now there's I guess the point was to say that there is kind of a root process that this creates that has a namespace, and we can bind these hidden devices to unhidden names. And we also pass in this context, which includes the process ID. So the idea was that you can create file systems that can look at the context and get a value out, possibly including the current process ID. And obviously that was helpful for the case when there's a file called self that's going to tell you your current process ID. Get that from the context and then output it. So that's what we see here. And inside that process, proc1, there's an NS. If we look in that, it goes back to FS and proc. And if we look inside proc, we get 1, and then we see NS again. So this is expected behavior that you could loop like this, but it was not working before. But this is the kind of thing that takes some massaging to get working. So anyway, now that that's there, and then obviously bind functionality is here. So go back to our example and we try this out. If we were to do cat Wanix fsys new LOFS, then we get 1. There it is. And the only problem is that it is not bound yet, or it's not mounted. So we just see the control file and the type. So if we echo mount into its control file, now mount directory that has the contents of this LOFS. And now the thing is we want to mount that, basically bind that directory somewhere else, maybe like data root. That now with echo, basically setting up a command. This mount will go in, will bind at data. And those paths have to be relative to the send this to our process control node, because it's really the process that manages the namespace that lets us bind stuff. And these bindings are per process, because that's the whole point, is every process has its own namespace, so bindings are per process. So we send this to the process control node, and so now in Wanix there's the data directory with hello file that we can from. So that was the original goal. We created an in-memory file system, and then we bound it to a directory. So all the basic mechanisms of we've got these primitives to create file systems, created a file system, and this process, kind of a placeholder file system, but lets us create an empty process for this situation where we're using Fuse. And that's basically all I wanted to get to before we now start trying to get this to work web context. Which is, originally what Wanix was for, but the fact that you can use Wanix to sort of programmatically create, new file systems on your actual host system is a powerful thing. So I like the idea that you can use it in both contexts for different things. Does that make sense? Did you kind of follows from the last week, right?
Yeah, it's like a lot of pieces right now.
Yeah,
But
it's all.
it it
It
makes
took
sense.
us
It's
like
just like
four, I guess we worked on this more than 4 days because I worked on it between streams, but now we have these basic primitives of, file system devices, processes, sort of an abstract concept of a process with namespaces, and being able to bind use the namespace of the process via the file system. So everything that we've done, we can do through the file system, right? These primitives that we've made, we've exposed. There's kind of realization watching some of the Plan 9 videos. We had a watch party, and during one of the talks, I realized one way to think of it is the Plan 9 kernel is exposing most of its functionality. Normally a kernel will have syscalls that like libc wraps all these syscalls, or eventually something calls syscalls into the kernel, whereas with Plan 9 most of the syscalls are just file system operations, and most of the functionality of the kernel, doing networking, doing audio, working with mouse, working with devices, all of that's done through the file system. But the file system is sort of composable and layerable. So because you could always layer your own version of the network file system in Plan 9, you're sort of overwriting the kernel functionality. So in that way, it's sort of, because it's exposing functionality of the kernel through the file system, and the file system is sort of customizable, that you're able to effectively customize functionality from the kernel, making the kernel sort of customizable. If that makes sense, if I use the right metaphors. But like, there's an audio device, and then you could always make your own version of the audio device and then kind of bind it on top of the audio device file. And then maybe that audio device passes on the data to the actual kernel device file, but in the process, it does a low pass filter, some audio filter, or normalizes the volume or something. So it lets you add filters, this idea of interposition, where you can kind of I don't know how to describe this kind of architectural pattern, where you can kind of like layer things on top of each other, or like middleware, I guess, is one example. The idea of middleware is code that actually, have you ever heard the term middleware? Either of you?
Yeah.
Yep.
I mean, I guess, yeah, I mean, it's a pretty good name in that it sort of like sits in the middle. And so in that way, we can create middleware for, anything on your system in Plan 9. And so that's where we're trying to get to. And we have those primitives now. So making it work on the web. I actually wanted to show you guys one more thing, because before we started, I made a paper prototype, which is kind of like Perry, you know what a paper prototype is, right?
Yes.
I guess the idea comes from like in UI design. You might draw or print out, a paper version of the UI, and then you can kind of present it in front of users to test it without having to actually build the thing. So it's that kind of idea of low cost validation and low cost experimentation. And so I did a whole paper prototype of how I wanted to use Wanix before we even started. So I can show you that, because we're now pretty much to the point where the paper prototype is almost real. Let's see. Sir. Oh, it's not actually. Tell me. So I'm going to show kind of a demo that basically this paper prototype was designed to make a sort of demo. So maybe this is what it would look like once Wanix, this iteration of Wanix is released, what it might look like. But so we're imagining a scenario where we've loaded Wanix onto this page, and we're going to interactively kind of play with it. So there's a Wanix class. We'll create an instance of it. We don't really know what it does. I mean, we've been playing with it on the command line. What is it doing in the browser? Well, this Wanix object has some methods on it. It'd probably have a lot more, but see that like it basically looks like a file system. Like we have these high level, we can read a file, write a file, read a directory, check if it exists, and there'd probably be more because these are just high level versions of file system operations. So maybe if we call readdir, we can see what's going on in here. So all of these are async, so we'll have all await. So the root directory of this Wanix object has a bunch of stuff in here. Like we've seen fsys and proc, but there's also term and dom and VM. You can see it kind of works like like what we've been doing so far, although it looks like there's some other file systems in there. Let's make a hostfs. We'll set up a variable based on reading the file fsys new hostfs. Oh, and immediately it has us pick a directory, given that this is the browser's sort of file picker for opening up a file system directory on your host computer. Pick something and give it permission. The fid now has 1, And fsys now has, look at that. We could name of the directory that we opened, and we could even, like we've been doing on the command line. In this case, though, it was to the file systems control file, do a bind there's a data directory. And again, this is all fake. I'll show you the source for this, but this is basically a way to kind of walk through, how the system might work. And so that's kind of the basic stuff. And so now we can do something that's more specific to the web. I mean, we already saw opening a picker from the browser, but there is this terminal directory or device, and we can create a read file on as a PID and write to term1. I just made up a command, attach DOM device, which, as you can imagine, might be a reference to the current page's DOM. So what that did is that created a xterm.js terminal and attached it to the page's DOM. So we're sort of dynamically impacting the DOM that we're on. Let's see if we await. We can see that this device has a couple of files, not just a control file, but also a data file and an in and an out. And we could actually use those. If we term out, this is the output of the terminal. And so if we write to it, it writes to the terminal. And because that's what a terminal is it's just a dumb sort of like display. You can, write to its input and it collects input with keyboard. That's the idea of a TTY in the Linux world. They used to literally be physical terminals, and then they became virtual. We could also send a the terminal. But then there is also a VM device, and obviously it's a little annoying to have to write this as JavaScript. We're kind of doing what we do on the shell, but without, but it's a little more verbose because it's JavaScript. We have to type await. And on the shell, we could do a lot of this with cat and echo and ls. So wouldn't it be great if we had an actual shell? And we can do that by setting up a virtual machine or an emulator. So here we'll do await read new alpine. In this case, and again, this is just a made up prototype, but the idea that you could, in theory, create a virtual machine and choose its image or base image when you allocate it. So we got one. If we got a couple of things that you might expect, like image data, its root file system, and a control file. And one of the neat things that we could do is use the file system binding functionality. which is currently done through the file system CTL, but say bind, and we want to bind the VM1 TTY, which is the terminal. So, when you create a virtual machine, you can actually set it up to get a TTY device, which is basically like IO to the machine. It's like a terminal, how you control it. If you were to SSH in, it creates one as well. But for a VM or an emulator, there's usually some way to interact with the terminal. So here, this is TTY, and we're going to bind it to our terminal. It's data file. So effectively, what we're doing is that the input and output that would normally write to the terminal that we have on the page is going to be the exact same file as what lets us read and write from the VM. And so effectively that lets us give the VM a terminal. And so now if we were to start the VM and start, so we're sending a start command to the VM. Look at that. So the idea is from here, you have a working Linux VM, but what this is sort of the end of the paper prototype demo. But the idea is it would keep going because inside this VM, you would have a Wanix file system that is the file system that we've been working with. And so in that way, we use the file system to create a virtual machine, to create a shell that we can then use to more effectively use this file system. Continue to wire things up, but at least now we can do it, with a shell instead of having to do it over here in JavaScript. So that was kind of the goal going into Wanix, is like the first thing I want to do is be able to make this demo that I just did a reality. And so we have file system, we have proc, DOM and at least DOM, but a lot of the rest of this is very web specific. And so, we need to get Wanix working on the web. That demo makes sense, though?
Oh yeah,
Um,
it was interesting to see how it's working.
it's sort of
I'm like just quite...
bootstrapping itself into existence.
Yeah. That's what my thinking went to. Like, is there gonna be like a terminal for Wanix, or Wanix is also gonna run on a is there gonna be some UI or something?
Yeah. So the idea is that at least as a starting point, you can use this instead of, the old Wanix, which we had to build a shell and all this stuff. Here, we're basically using the fact that we have, or we can have, virtualization built into it, or at least emulation built into this system, that we can use that as a way to get a shell
Okay.
that we can use. So it'll probably be kind of a custom, really tiny Linux that will come with Wanix that you use too. And more or less everything that I just did would be done for you as a user of Wanix. But this is to show you that, that's how it's sort of bootstrapped behind the scenes. And that you can use a lot of these primitives to do other things. You could create other virtual machines, create, kind of a Docker-like system that, builds custom environments and stuff like that. And those custom environments would then be used for basically Aptron behind the scenes. And now you can start to see how this new Wanix ties back into Aptron, because Aptron doesn't load on this browser for me right now, but normally there's a terminal here and it has a Linux system and, a little VM. But now this VM will be sort of managed by Wanix, which will let you then create other VMs through the file system. So now we have to make it work on the web. That was a fake prototype. The source code for it looks like this. The Wanix class and all of basically I wrote a script for what the demo would look like.
Oh.
And then basically implemented each of these methods, because there's not that many: read file, write file, and read dir, and just have conditionals, if you put in this, and just kind of make it return. It did some dynamic stuff, like, if you read a host new, it'll show the directory picker and it will add stuff. But it's just kind of interesting, sort of faking it, although it does actually set up a VM and everything. But anyway, that was just to help visualize, where I'm going, and I could show other people and get an idea of where we're going. And that was made before we started anything. And now we're almost there. So I started a new WASM package here, and it's really just kind of experimental, because one of the things that I'm doing is v86, the emulator that I've been using, that was used in Aptron, that's used in NV86. In order to get that file system, in order to get the Wanix file system usable from in the VM, we have to mount it in somehow. And it's kind of interesting because v86 is often set up so that the root file system is replaced with a 9p mount, where in the emulated system it uses 9p, which is actually the same protocol that Plan 9 used. For some reason, emulators have picked it up as a way to communicate file systems. It speaks 9p to a 9p server written in JavaScript that then loads files over HTTP. And that same sort of hook, or that same kind of bridge that they use to get files over HTTP, we can use to instead get files from Wanix. But it's required me to have to do some modifications to the v86 file system stuff, and I've been debugging that. So I already have effectively a version of Wanix that's running in the browser with WebAssembly. And that real quick before really get into it. So in this WASM directory, we have a main.go that we compile with TinyGo. And TinyGo is another implementation of the Go compiler, but using some more traditional approaches. TinyGo is not written in Go. And so because of that, it kind of works with other C libraries, and I guess they can ultimately the point of using TinyGo for this is TinyGo is able to produce smaller binaries because it can effectively do pre-shaking and cut out a lot of the Go runtime that isn't used. TinyGo is also used for the same reason to do embedded Go on embedded devices, of what it's known for. But it can also produce WebAssembly binary. So this main.go started as me just doing the same stuff we did in our command line thing. We create a kernel, we set up a HelloFS, create a root, find these built-in devices to names. And then other than that, we're just kind of setting up a way to communicate between Go and the page, which we use duplex for, same as, the extension here, sort of my general purpose communication stack. And so far, the idea is to implement some methods that would be exposed over duplex that would then call their equivalent thing here. So readdir just calls readdir on our namespace and changes some of the output just for formatting and stuff. But effectively, a lot of our file system operations will be exposed over this. And then in our JavaScript, we can set up a message channel and a new Wanix class that just sets up a duplex connection over that channel and then provides a lot of those methods as JavaScript methods, and they're just wrapping calls over RPC. So this is incomplete, but you can see that I've been getting started here. And then after that, we do some incantation to basically load our WASM module in the browser, which also depends on some JavaScript that TinyGo comes with that helps set up the bridge between the Go runtime and the JavaScript environment. Anyway, so that's one part of it. And then I've also been testing my sort of hacked version of v86. So we're also starting a VM in here. Yeah, I guess we have a little demo of this. This is sort of a little bit out of the order of operations that I wanted to do on stream. I was trying to get ahead, getting this integration with 86 working. Get in there and we can so it's booting up the Linux kernel, and then it's gonna start an Alpine Linux image, which actually sets up its root file system over 9p to a file system that's implemented in JavaScript. It's actually a full, just like we've been doing, we've been making file system abstractions in Go. This is a sort of a virtual file system implemented in JavaScript that has inodes and everything, and it's exposed over 9p to the VM. And so in this VM, all of this file system is actually served from this JavaScript file system. And so the idea is that I was going to sort of create a new instance of this file system. Actually, it's down S2 right now. And kind of just override some of the functionality to then basically call Wanix using the methods that we expose. So the way I'm debugging this is actually letting the file system set up as usual for the VM, and then I've mounted this FS2 as a file system under this file system, because while I'm working on it, it's not gonna work entirely, so we couldn't just mount the root file system and have it work. So in order to like develop it, it's mounted as a subpath for now. In here it has a foo and a bar directory, which we created by code here just to kind of test that out. And then what it currently doesn't do is it doesn't know what files are in the Wanix file system until you actually try and access them. So if we did an ls fsys, for example, you can see this is our Go code. Apparently Linux is trying to look up mail path in all of these directories. I don't know. So here it did an open on fsys, and so now there's an fsys directory in here. Unfortunately from there we can't see, but basically that fsys, even though there's no way you could know that that's any different from these just empty directories we created by code. Fsys is actually coming from our Wanix directory, from our Wanix file system. So that's a start. And now we have to kind of fill out the rest and get it to work. But that's actually a lot harder to do, so I've been doing it off stream. But obviously, proc or oh, it's a directory. Proc there. So yeah, that's kind of where that's at. This bridge is kind of the last big piece to getting Wanix to show up in the VM. So anyway, that will continue, but there's still other stuff that we have this Wanix class, and we have a bunch more methods to wrap here, and there are some other things that we could make that don't have to do with the VM. For example, in the paper prototype, there was a DOM device. So that would be something that lets us interact with the page's DOM. So we could work on that. In fact, that's probably what we'll do today. And at some point we had to make this terminal thing, although we might be able to skip that. And just kind of hook the VM terminal directly up to an xterm in the DOM. So